Hello, everybody, and welcome to this week's SEDS Online webinar. You are stuck with me, Valentin, for this week. And before we just crack on with today's webinar, I would like to thank our sponsorship from the IAS, which allows us to offer all of these resources for free. And make sure to check out our website if you want to have all the latest information about upcoming events and meetings. And don't forget to join our coffee breaks. So today's lecture is by Dr. Lilian Navarro from Cape Breton University in Nova Scotia in Canada. Lilian received her bachelor's degree from the Universidad Central de Venezuela. And after that, she moved to the University of Ottawa in Canada, where she obtained both her master and her PhD in sedimentology. Lilian's current research focuses on Neoproterozoic deep-water sedimentology, more specifically on the origin and stratigraphic significance of phosphatic and mixed siliciclastic carbonate sedimentary strata. And today she's going to talk to us about submarine channel lobe transition zones along an ancient passive margin. So Lilian, the floor is yours.
Okay, thank you, Valentine. And first, before I started, I want to thank SEDS Online for allowing me to do this presentation. And I also want to thank everybody who have come to see this webinar. The idea today is I'm going to take you to a very short, but surely nice field trip to the mountains in the western of Canada. And specifically, I'm going to talk a lot about this interval that you see right at the background. But before we actually started, let's start talking a little about when we are looking into the different sediment routing system in this water setting. What we always find in most of the research that has been done is always concentrated here in the slow channels and the channel levee systems, and in the other end member, in the low system. We have a very little amount of work done in between them. And that is what I have been, I don't know why. Okay. And that is where I want to focus more today. I want to discuss about what happened in that area where we call the channel-lobe system. And this area is typically occurring at the base of the slope. These areas is where it takes place what is called the channel-lobe transition zone. And this is a term that was coined by Muted at the end of the 70s. And there has been basically every decade a good grade of contributions that have come in, people working in the CLTZ, which is the short for channel lobe transition zone. Many of these people have been working in different parts of all around the world in modern and ancient systems. And this is what we now, I just put a timeline of many of those contributions. But one important contribution was actually early in the 2000s when Wind et al. And his colleagues, they gave us a picture how that the CLTZ looks like in modern system. And they did this representation where they show us, okay, in this area is completely populated by scours. And also there are sediment waste and localized sands and reworked materials all across the area. And this has been the main figure that many people who has been working in the CLTZ have in mind since then. This looks great, but how can we recognize the CLTZ in the outcrops? And that has been a little bit more challenging. If you have an outcrop that allows you to do a three-dimensional view and you can reconstruct what happened up dip and what happened down dip, up dip in the slope and down dip in the basin, you should be able to recognize some indication of the CLTZ. Especially if you find in those areas numerous scours concentrated in one place. Another criteria that has been used is that, well, the CLTZ can be expressed by the screed surface of multiple erosion and bypass, and that surface can appear when you have the lobes and you have a channel right on top of it. More lately, there has been other indicators and has been bed forms and associated with supercritical flows or backfill structures. And in some cases, some people have recognized megafluid surface, or they also has recognized, and in this area, sometimes you find coarser grains sediment and is coarser in comparison with the one that you see down flowed in the basin. So now we're going to start our quest, and I'm going to take you into the Windermere turbidite system. This was a turbidite system that crops out in the certain sort of Canadian Cordillera, specifically at the Caribou Mountains. And this system was formed during the breaking up of Rodinia when the Paleo-Pacific Ocean was created in the Neoproterozoic. This system cropped out for, it is estimated that the area is more than 30,000 kilometers square. So this is a large system. That is the place where I work most of my, for this project. And I'm going to show you part of what I did in my PhD. These PhDs, I did it at the University of Ottawa under the supervision of the Professor Bill Arnold. Here are the two localities that I visit, Mount Quanstron and Casa Creek. Mount Quanstron is approximately 360 meters thick, and Casa Creek is approximately the area that I work. It was approximately 290 meters thick. Now, these locations are, this is the Jasper National Park. It's approximately 250 kilometers from the national park towards the northwest. And if you are driving from Calgary, it's approximately 7 hours, and plus an helicopter ride or a very grueling hiking. Now, what I did here is I measured more than 4 kilometers of section through all of these, in these localities. The beauty of these places is that they are glacially polished. So these glaciers has been retreating fast in the last decades. Every time that we go there, there is more new and clean outcrop. And we are able to see not only well-preserved the coarser, the sandstones and the conglomerates facies, but we also see beautifully preserved the fine-grained strata. And in this, when I was working in this area, another good things about is that everything is vertically dipping. So I was able to walk the buried contacts and establish what are the significant surface. So I have a really nice and well-constrained setting to work with. What is a stratigraphy here? It's very simple. We have two stratigraphic units to deal with. One is the upper Casa group, and the other one is the Isaac formation. In the case of the upper Casa group, is approximately 800 meters thick in Casa Creek. Most of it you see the sandstone-rich sheet-lized deposits that are interpreted to be basin-floor deposits. And the Casa is overlain by the Isaac formation, which is the lower member of the lower Caribou group. And here is a more than 1.3 kilometers thick. And what we see there is that we have these sandstones and conglomerate filled ridges, and they are encased in mud, and well, we call it mudstones, but it's basically embedded turbidites. And these ridges are showed lenticular intervals that we have interpreted to be the channels, slow channels. Additionally, in this area, we also have one unit and is called the first Isaac carbonate. And this unit is very important because it's actually a regional marker and it's a mixed siliciclastic carbonate unit. So what I did for this project and what motivated us is that based on all the work that has been done here in previous years with different students, we knew, and also in my master's, when I work for my master, we knew that down in the casa, we know what are the main elements that has been recognized. So we see mostly splays and sheet-like splays that are interbedded with fine-grained deposit. In the ISAC is mostly what I already mentioned, slow channels and mass transport deposits that are encased within fine-grained deposits and mostly levees. Now, what happened in between those two units? Because there is a major change in the architecture that is occurring here, and it's also there is a major change in the lithology. So that is the motivation. What we start here is looking at and try to characterize and establish the facies and the stratal elements in the kit. What I call the kit is a casa-ISA transition interval. Based on then we see that major drastic change, we were also looking into the idea that was like, can we identify channel-lobe transitions on deposits, or what exactly, or just base of the slow deposit, what can we find there? The goal, of course, is we try to understand what are the dominant depositional and erosional processes that were taking place here, and how and why we see this dramatic evolution from the casa, from the basin floor deposits and the ISAC and the slow deposition. From now on, most of the work that I'm going to show you is already published last year, finally got out, and is this is the publication in the Sedimentology. And I'm going to give you from here in the rest of the slide just a summary of many of the key observations of what we recognize there. And as you see, the paper is slightly lengthy, but it's because there is a lot of good data and I was trying to compile in that paper. Some of the colors in the diagrams that you are going to see in my next slides are the color scheme in the paper is slightly refined and subdued, but it is exactly the same information. What do we see here? First, it is, regarding to the facies, what we see a lot of, many of these, yellow colors is very sandstone-rich units. What we have is that we have a suite of a spectrum of facies. We find from coarser grains, conglomerates and coarser grain sandstones that were deposited by high concentration turbidity currents to fine-grained facies that are just interbedded sandstone mudstones that were deposited by interpreted to be deposited by low concentration turbidity flows. And we also we find debris flows that are we interpreted from the matrix support, matrix rich conglomerates. One thing that we first, even though that I was only working in that interval, I also walk around what was happening below the interval and above the interval. And one surprising thing is that we see that there was two major changes occurring exactly in that place. One, where we started is actually below that is the thickest mudstone unit in the upper Casa group. And it is when I recognize it in both places, in Casa Creek and also in Mount Quanstrom. And the other thing that I found is that right at the top of the interval, we have the first mass transport complex in the ISAC formation. So all of those sandstone stripes that you saw in the first figure is actually the next step for me was to try to, okay, what exactly we see there, what is what are the main elements. And I recognize 9 different elements within that area. So even with the colors that you see there, is already telling you that this is an area that have amazing heterogeneity. Further down, I have to, after I define, okay, what are all the elements within this place, I was able to break it down and I use a very easy hierarchical arrangement from small to large. So I define the elements, which are established by a clear bounding surface and a distinctive facies. Those elements are when they stack, they are going to be called units. A complex is just comprised of several stack units. Typically, the units they can be traced for several kilometers laterally. The system overall is composed of several stack complexes. And at that level, I see the 3 complexes that I'm going to show you next. Those 3 complexes are found in both localities. But let's start first with few of the elements. I'm not going to be able to go to and show you the details of all of them, but I'm going to show you the most important and the common dominant elements. In the sandstone-rich sheet-like deposits, we found splays. And how do we recognize those splays? Those splays they are laterally continuous, they are a kilometers scale. We can see that those splays in some places, they are highly amalgamated. This is 100% amalgamation. But when you walk laterally, you are going to, at the large scale, is when there is a gradual fining and thinning laterally. In the next element that we find, even though then everything looks like sheet-like deposits, and that is what I put it in quotation, I recognize numerous distributary channels. And this was a very interesting finding for us, because where we walk down in the rest of the upper casa, we have few places where we already identify distributary channels. But when I start working in this interval, it's actually there are distributary channels everywhere. And the beauty of this outcrop is that it allows you to see the channels are shallow and narrow. We are able to walk from the center of the channels, and we are able to see in some places how even the channels fine and thin. We are able to walk that kind of contact. These channels showed, even though they showed that all gradual change, but the fining and thinning, vertically within the channel is not as drastic as you always expect. It's actually more gradual. These channels, in some places, they are just stuck, and in other places, they can actually show a more interesting nested arrangement. And this was a very surprising realization that what we see here in some of those sheet-like deposits is actually just a bunch of distributary channels cutting into each other. They were distributed all over the place. So how do we interpret this? Well, it has been already recognized in other places that distributary channels and common in proximal lobes. And here I show you an example offshore Indonesia. And in this case, we have a network of distributary channels, and they are thinning and ending into numerous sandstone-rich, sand-rich splays. So this is not uncommon to find. And one thing that we see is that there there is a big similarity in the dimensions of the units that I established in the outcrops and the distributary channels and the terminal space and were defined in this example in Indonesia. So that was kind of encouraging to see. Now, the other element that we recognize are scours. And yes, they are also one of the most dominant feature to recognize in this area. The scours are well defined by the erosional surface, and the filling of the scours can be with variable facies. It's mostly sandstone-rich fills, but in many cases, it's just you have abundant tractional structures. How do I separate the distributary channel for the scours? The scours doesn't show that lateral change or vertical change in the filling. So those is a clear separation for how we see them. Locally, we find scours that have a very spoon-shaped geometry, or there are scours that are actually filled with mud. So one thing that I want always to mention is that sometimes, even though that we see that the majority of the scours were filled with sand, sometimes you also are going to find other type of facies. And last but not least, we also recognize scours that are not just few meters deep. It's like scours that are several meters deep, and we can trace those for hundreds of meters. So these are laterally extensive scours. We call them the large scours, and we found two within the interval. One of the scours have a sandstone-rich filling. This other scour is actually a beautiful scour because you can walk above the erosional surface. You can walk laterally and you are going to find a suite of facies, which is suggesting that this scour was the results of multiple flows that were passing through here. So what we have at the end preserved probably is not, it's just a spare material from what actually have moved through there. Scours are common in CLTZs in many of the modern systems. And here I show you an examples at the mouth of the Agadir Canyon, where they have recognized scours that have up to 1 kilometer wide, and those scours could be even 20 meters deep. So that is not uncommon. And it has been actually reported that some scours, especially in the modern system here in blue, they tend to be quite large. They tend to be up to 100 meters deep. And I think the wider is 9 kilometers wide. Commonly, what is reported in the outcrops is more scours. As scours, they tend to be less than 10 meters deep, and they tend to be just few tens of meters wide. So I plot all of the different dimensions of the scours that I recognize in the CASA as a transition, and it's kind of like I have a suite of different dimensions, and it fit from what it has been recognized in the outcrop, but it's also some of these scours are actually can be comparable to the ones that has been recognized in modern systems. The last element that I want to point out are levee channels. And I recognize within the interval, the first levee channel actually it define the contact between the CASA and the ISAC. These levee channels it shows laterally accretion surface is the filling of the channel is actually pebble conglomerates and coarse-grained sandstone. And we have in the channel that we are able to actually, in the upper channel fills, we are able to walk from the channel's axis all the way to the margins we can also see the levee facies that are contiguous to these channels. That channel is cut locally by the slide, but is the first actual slow channel found in the area. And this channel showed a clear migration towards the northwest. So what I have recognized is that in the larger scale, at the complex level, I can separate this interval in three parts. The lower part is actually capped by a debris flow that I found in both locations. And what do we have here is that it's just mostly composed of abundant distributary channels and small scours. And I also recognize the first large scours in this area. The second complex, the middle complex, is considerably thick in comparison with the other two. And these are more than 178 meters thick, and in Quastron is actually thicker. And what we have here is a suite of distributary channels. In some places, they are on top of terminal splays, and the scours are everywhere. And right at the top of the complex is where we have the first slow levee channel of the Isa formation. And last but not least, I have the last complex, the upper complex is actually, this complex have a very similar composition, not composition, but it's have a lot of similarity with what I showed you in the first lower complex. But because we have abundant small scours and distributary channel plus the occurring the second large scour. This complex was actually truncated by the first mass transport complex in the Isa formation. And if you guys want to read more about that mass transport complex, there is a paper that I published we published a few years ago about it. So I will recommend if you are interested more about what is this complex made of. So now that we have, I already showed you all of the architectural variability that is expressed within this interval. I want to go and show you there are a few more changes than we see within that interval. Looking at here, this is just the transition, the contact between the Casa and the Isaac. And the rocks, you know, if we go from here down, most of the rocks are going to have that color. This is just like a greenish or really light pink color. When you look at it in petrography, these are just siliciclastic rich strata. Now, and those are what is characterized the lower and the middle complex. Now, when you arrive in the upper complex, the rocks, the colors of the rocks, you see this orange. You're going to, in some localities, some places it's going to be a deep red, or it could be brownish color. So this is a very interesting change. And this is a regional change that is occurring across the Windermere, the entire Windermere turbidite system. And when you look at it in thin section, what you recognize is that there is a high proportion of carbonate cement in these rocks. So we, what we interpreted, when we only see the carbonate cementation, we also found locally carbonate class within some of the strata. Here, some, you will see a lot of bits of that reddish, brownish, orange color. And that carbonate is quite important because it's telling us that this is no longer, we cannot consider just a pure siliciclastic system. There is a change, and we start getting some mixed siliciclastic carbonate sediment into the system. So one thing that I did, we did is, okay, where exactly the carbonate star appearing within the interval? And I went down, up and down, until I found that definitely the carbonate star showing up in the channel field. And thus is not as higher in proportion as the ones in the upper complex, but there is a good amount of carbonate class within that channel fields. So at the end, how do we put all of this together? What's going on here? And this is where we have to step back, and what we need to start thinking is what we interpret here is that we have two different scenarios. We think that the lower complex and the upper complex are what we could be comparable to a detached channel-lobe complex, where the CLTZ was well formed. While the middle complex is what we think then is a different type of a channel-lobe configuration, because what we think is that in this case, the CLTZ didn't form. It was just that the channel and the lobe were close, were attached to each other. How do we explain all of these changes in the configuration of the channel-lobe architecture? What we think is then what is playing here is the flow character is changing. So in the case of the lower and the upper complex, the flows that were moving through here, they were highly erosive. They were able to bypass and start sculpting that channel-lobe transition zone. And then they actually deposit further down in the basin. Now, in the case of the middle complex, what we think is that the character of the flow was was more depositional, and all of the flows that were moving through here, they were just dumping the sediment right close to the channel mouth. And they were then spread it out and creating that spaghetti streams that we see in that example of the Gulf of Mexico. And further down, the place where actually develop. So how do we put this together in the stratigraphic, the evolution? What we have is that we interpreted that there are major changes in the configurations and these areas. And what we think is that when the first detached channel-lobe complex was created, we have a reactivation of the coarser grain sediment that was coming through into the area. And this probably coincide with an onset of the falling relative sea level. For the second complex, we believe that this complex was probably formed during the low stands or the transgressive conditions. And in that case, the sediment, it was still highly the siliciclastic, but the fact that we were finding those carbonate class especially in the channel, it's an indication that there was something going on up in the shelf, and there was a carbonate platform that it was creating. So we think that that carbonate platform was incipient at this point. And last but not least, the detached the channel-lobe complex was creating when the sediment was actually more intermixed. We have the new introduction of sediments and carbonates in this system make a big deal in the way that the flows were behaving. They became, they were more efficient to move through the areas and to actually move the sediment basin floor. Another thing that we find, that we see evidence of early carbonate cementation in these rocks, we also believe that the slope was becoming slightly highly cemented. So that could also help to create some steepening in the slope gradient for that during the time that this complex was created. And all of this was occurring while in the long term was a progradation of the slope. taking place in the Windermere turbidite system. So that is the overall picture of what we think can happen here. Now, one more thing that we did is that we were started looking at, okay, this is a very interesting idea that was happening in the Casa-Isa transition. Now we were looking into other cases around the world in modern and ancient systems, and do they compare to what we see in the Windermere? And this was quite surprising. Well, one thing that we found, and is the CLTZ architecture depends of different factors, and what is already reported, there is a interesting contrast. Most of the work that has been done in the ancient examples are from active and intercratonic settings, while most of the modern examples that has been reported were actually formed in passive margin setting. So in this case, the data set that I show you from the Casa-Isa transition interval is quite unique. And it's interesting to see. Why is this important? Well, because many of the CLTZ in the ancient that they have been reported, they tend to be quite small in size. The ones that has been reported in the modern examples, they tend to be 20 times larger in comparison with the ones in the ancient examples. So this is kind of important to keep in mind when you are looking at this type of system. And also one thing that we see is that, of course, the tectonic setting seems to play an important role, because it seems that if you have a large system, you're going to have a large channel-lobe transition zone also. Last but not least, we were also looking at is, okay, so what exactly, because I show you an example where we believe we have detached and attached system. How do people see then in the literature? Some of the things that we recognize is that commonly most of what has been reported are always detached channel-lobe systems. There are very few cases where it has been reported, whether it was modern or ancient, where they find a system or they have recognized in the same system that there has been have different stages of detachment and attachment within the channels and the lobe. And as I show you in this example for the Casa-Isa and interval. So at the end, what are the main takeaway message that I want to give you is, when we were looking into the Casa-Isa interval, we found that the characterization of this outcrop gave us an idea that there is a lot of complexity in this type of interval. We see it recognized here 3 different architectural assemblies that start vertically, and there are changes in the elements proportions and in the grain composition that seems to be associated with the changes that happen in the configuration of the lobe, the channel-lobe system. We see that the channel-lobe transition zone changes through time, and that is and it's also changed spatially. Last but not least is what is controlling this dynamic evolution. For this case, what we propose is that, well, there are some major changes in the sediment supplies that are affecting the way that the flow are behaving. It is affecting the character of the flow, and it is affecting also the efficiencies of the flow of moved sediment. And also, we also propose that there are some changes in the slope gradients, and overall, there is a major reconfiguration in the whole turbidite system, because it was the prograding in this, at least at this point. And without further ado, I just want to thank everybody who has stick around. And if you guys have any question, please feel free to ask me.
Very impressive presentation and data set, Lilian. I see that Jaco, we already got a question from him in the chat. So, muchas gracias, Lilian. I was wondering if you found any hybrid event beds anywhere, especially in the channel-lobe transition zone. If so, in detached, attached channel-lobe transition zone, or both? Jaco from Wales, actually, that was my exact same questions.
So, okay, so here is the thing. We don't call them hybrid event beds. When we were measuring, we called them the matrix-rich sandstones. So yes, I find them everywhere, matrix-rich sandstones, especially in the inter-scour areas outside this, between the scours. Yes, so in the distributary channels, they're also below the distributary channel. In the we separate them. We sometimes in some localities we have avulsion splays below the distributary channels, and we also find matrix sandstones. So yes, they are everywhere.
So before I just want to quick jump into this question. Do you have any like specific areas or you know, time, like I think it was basically what Jaco was asking, either you see more in the detached period of your channel transition zone, or do you see them more, these hybrid event beds, you see them more when the channel this zone transition zone was attached?
Yes, I find that it's kind of I find it in both. Of course, the thickness of the attached system is quite considerable in comparison with the other two complexes, the detached complexes. So I find that, yes, the proportion maybe looks, I find it in both. The proportion maybe looks more in one, but I think you will find it in both.
Okay, that's I'll have another question after this regarding this. I think we have Marek who's about to type something from Krakow, but yeah, there we go. Marek is there. Marek from Krakow, Poland. Fascinating. Now, is there any specific part of the system in which dune scale cross bedding and hopefully dunes themselves are present?
Yes, dunes are not that common, but yes, we do have some dunes on eye angle cross stratifications. Yeah, there are some and some of these are actually filling scours. So yes, there is a lot of traction structure.
All right, cool. Then we have Ross Campbell from Queen's University in Ontario. Interesting talk, thank you. How do you interpret the red and orange beds? Are they iron oxide orthogenic, clastic, or due to later alteration?
Yeah, so we have here this ferro and calcite, and it is already recrystallized because these rocks has been undergoing into low-grade metamorphism, but we do see some evidence of multiple generation of cement within the rocks.
Okay, that's actually a good transition to Robert Handelford from the US, who says, very nice talk. Can you say more about the character of the carbonate clasts?
Yes, so the carbonates, at least in those carbonates within this interval, they are just it's just calcite rich. It's just mudstones, but not here, but in the first isocarbonate, I do have found evidence of more shallow platform carbonates.
All right, and Next question from Pete Burgess from Liverpool. Great talk, thank you. Has anybody offered an explanation of why the scours form in the channel transition zone? If I have understood correctly, it seems like a lot of erosion occurs just before the position of lobe strata starts.
Yeah, there are a number of papers that has been published and really good experiments that are starting done in what is going on in the channel-lobe transition zone. Some has been explaining it because in these areas, remember, we are moving from a confined setting into an unconfined setting. So here the flows are, some of the flows are undergoing to hydraulic jumps, and there is also a really good paper that is talking about the, we call it the flow relaxation. As soon as the flow get out of the channel mouth, start actually, it's like a bulking and relaxing process, but is allowing also to create a lot of interactions with this substrate. So yeah, there is some literature that you can look more into that.
All right, then we have a question from Sebastian Kampfe. Says, hi Lillian, thank you for the amazing presentation. Were you able to observe the contact between channel fill and overbank levee facies? If so, what its nature? Sebastian Kampfe from Chile, in Virginia Tech, studying the slope channels of the Great Tres Pasos Formation.
Okay, so yeah, so we do have some, I will have to say that there are better examples of levees up in the section. There are a bunch of papers that we are actually publishing lately in the research group that you maybe would like to see. Yes, I do have, I have only one channel-lobe levee channel complex in the interval, but I can give you some of those reference if you want to make a clear comparison with the lithology, because they are quite detailed.
Yeah, and then I'm sorry, my chat had just jumped, and Jillian just a comment on Pete's question, and she says, as I see the channel transition zone, it is a zone of bypass, but has the position as well. Scouring is, I think, a response to changes in the rate of change of gradient.
Yes, of course, because if we are moving, we are passing, there is, I find that that is another of the factors that is happening there. And that is why they explain it with the, it is explained with, then in this area is occurring the hydraulic jumps.
So maybe on this, how amalgamated are your scours between the two? You have the two zone and at the bottom and the top, and then you have this thicker zone in the middle. So are they more amalgamated? I expect them to be more amalgamated at the bottom unit and the top unit than they are in the middle.
Yes.
Right. So
yes, because that is one thing that is those are the complexes where I found the largest scours. In the lower complex is where you actually see is locally highly amalgamated, but the second scours is not, it's just a bunch of discrete fillings above the surface.
Okay, so, and you explain this by just having this thing unconstrained, right?
Yes.
Rather than having an increase in subsidence.
Yes, yes, and it's
okay, cool.
There are some good papers that have been showing in mother sister that they have recognized when we, a few years ago, they saw that in the scours, what we think, it's like they were tracking in a mother system, and the scours that were passing in one time, they fill, they left some filling, and the next subsequent flows actually erode completely what is happening. So yeah, this is a very active area. I find that what I see now is not necessarily what it moved through the surface.
Yeah, I think basically this channel transition zone had sparked the discussion. Just a comment from Pete now, we can reproduce the scour in new numerical models. It has nothing to do with gradient changes in these models at least, but it is rather interesting and counterintuitive effect. Hopefully we can present soon on how it works. Well, yes, hopefully
Okay,
too.
yeah, of course.
Very interesting.
It will be interesting to see. So that is why, like, we think that I think that there are several factors and it's happening in that location. It's changes of gradient, and in this case, I kind of like a leaning into the flows. For us, it's just in the flows, the changes in the flow character. It plays a good. It is a good. It can have a good role.
All right. Cool. Then we have another question from Ross. What are some differences between these Neoproterozoic turbidites and modern ones, and how might they be explained?
So the thing is, I find that is in the case of the Windermere, it is hard to compare them. The dimensions in the, at least for the channel, for this interval, in the modern systems, some of these systems are quite muddier. And here I show you that we have actually a lot of sands preserved. So it was not overall what we have recorded in this section. It was not only an area of bypassing and erosion. We have a combination, like episodically, there was a lot of aggradation and deposition occurring also. And that is how it was, preserved. We have a good preservation of one of these elements.
All right, I think if anybody's got more questions, please feel free to keep them coming. Maybe I have just one last, maybe I just missed it. Do you have any time constraint on the duration of the succession you looked at? Or?
Okay, so this is I have one of our key details, because we have only 2 good constraints in ages, and they are not in this location. When there is one regional market in the Windermere supergroup, then is called the All 4 Point, and it has been dated as a 608 million years old. And then other marker is way up in the section in another unit, and that one has been dated as a 517 million years old. However, this is one of the things that I'm trying to get a date in some of the phosphate grains that I have found in this area. But this is a work in progress.
Yeah, super cool, super interesting. Mm-hmm. All right, before wrapping things up and thanking everybody, I just want to remind everyone of next week's talk by Anna Joy Drury from the University College of London, and she is going to discuss the controls and orbital pacing of Southeast Atlantic carbonate deposition since the Oligocene. And so with this being said, thank you, Lillian, thank you, everybody. Yeah, that was a great talk, Lillian.
Yeah, thank you guys for being here.
Yeah, see you all next week.